Hello students, welcome to Adantal. Good evening to all.
Good evening, sir.
Good evening, sir.
Good evening.
Sir, I want to say something.
Yes.
Sir, I request that when we are revising the previous lectures, then we are facing some problems. So, how can we connect, sir? Can we connect to you by any WhatsApp or any chat?
No, you cannot connect with me like that. But you can inform me that you are facing some issues. Then we can have a session on that. Earlier also I have conducted a session based on the problems given to me by the students.
Oh, sir. Okay.
So you joined late. That's why you are facing the problem.
Yes, exactly. I joined it.
So in which subject?
Sir, when I joined the kinetic theory, electricity and magnetism had already covered half. So, I am revising from the beginning. So. So some problem I am facing. So sometimes that problem, not the big one, but sometimes some little bit of issues that is being faced.
Okay, sir. What I will do is, we can schedule some session, especially for those who have joined late.
Good evening, sir.
Good evening. So I think that session will be helpful to all the students like you who have joined late. Isn't it okay?
Okay, sir. It will be very helpful to us. Thank you.
Yes. Let me plan something, but please let me know in which subject you are facing the problem. In electricity and magnetism.
At first I have to cover total part of the electricity magnetism, and after that I can that will be better for you and us, that I can accumulate all the problems, and then
that will be very good. So you go through the recording and let me know when you are done. Then we can schedule that session. Either one session or two session, it doesn't matter.
Okay, so now I am pointing the problems all over the subject, all over the topics.
Yeah, that is very good.
Okay, sir. Thank you a lot.
Okay, so students, today we have to start with kinetic theory and thermodynamics. So first of all, we will be discussing about kinetic theory. Of course, the complete name is kinetic theory of gases. And the very first thing that comes to our mind is, what do we mean by, first of all, a gas? A gas means something which flows. Actually, it comes under the common name fluid. These liquids and gases, they are a kind of fluid which can flow from one point to another. Okay, and of course, you know the difference between liquids and gases, so that I'm not going to discuss over here. And then generally, all the time when we come across problems related to gases, we use one equation which is called ideal gas or perfect gas equation. So what do we mean by ideal gas or perfect gas? Can anyone tell me?
So actually, which gases follows the rules of Boyle's and Charles law, you can say they are ideal gas, and who doesn't follow, they can be said.
So what property do you require in a gas in order that it classifies as an ideal gas or a perfect gas? That's what I'm asking.
Ideal gas condition, pressure decreases, the temperature increases.
Oh, that he has already said, na, that if a gas obeys gas laws. So there are various gas laws, na? Boyle's law, Charles law, Gay-Lussac's law, Graham's law of diffusion, Dalton's law of partial pressure, Avogadro's law, combined law. Of course, that is okay. But what is there in the gas itself? Is there any restriction on the gas itself or on the molecules or the entities of the gas itself? Of a gas, it is taken as zero. It is having point-sized molecules. Okay? An ideal gas. Yes, that is the very first point. And there is one more point that is very, very important. Without interparticle interaction, very good, Abhi. So these two are the major points that we require in a gas so that we can consider it as an ideal gas. So an ideal gas or a perfect gas is a gas, first of all, which strictly obeys the gas laws. The characteristics of an ideal gas are, yes, they are very good. Characteristics of an ideal gas are the size of molecule of an ideal gas is zero. That is, each molecule is a point mass, point size with no dimensions. Only then its size will be zero, when it is not having any dimension. And then there is no force of attraction or repulsion between the molecules of a gas. Okay, so this is the definition of ideal gas. Now, what is ideal gas equation? There is an equation to represent an ideal gas. Now, what is that equation?
EB is equal to nRT.
E is equal to nRT. So now let us give the meaning to these quantities. And can you tell me this relation relates which quantities to which quantities? There are two types of quantities. No?
Sir, pressure and volume to the number of molecules and temperature.
So what is their name in general terms? This pressure, volume that you are talking about?
So parameter of gases?
Of course, they are parameters, but a general name, very famous name is given to these quantities in general.
Variables, sir. Variables.
No. These are called macroscopic quantities. Macroscopic. Yes, they were. So, ideal gas equation. So we can say it is an equation which connects the macroscopic properties or quantities of a gas. And what are the macroscopic quantities? Pressure, volume, temperature, etc. Okay. So So it is a relation between these macroscopic quantities only. Na? Of course, with respect to physical condition also, because in some of the gas laws, we make temperature as constant, and in some of the gas laws, volume or pressure is taken as constant. So it will depend upon the physical conditions at hand also, that what kind of relation we will be having. Okay. But of course, there will be a relation always between these quantities. So a relation between macroscopic properties, for example, pressure, volume, and temperature of a gas, which describes the equation, which describes the state of the system, is called equation of state. And for ideal gas, this equation of state is PV equal to nRT, where n are the number of moles of a given gas. You can write it like this: of a given gas contained in a volume V. E is the pressure, of course, V is volume, V is pressure, and T is the temperature. And T is the temperature. Please check. Is it clear?
Yes, sir.
Clear, no? And what do you mean by R? What is R?
Universal gas constant. Universal gas constant.
Universal gas constant. So let us call this equation as number 1, and this is an ideal gas equation, or perfect gas equation, for n number of moles, for n moles, simply. Okay. And for 1 mole, it becomes PV equal to RT, na? If n is 1.
Yes, sir. Yes, sir.
So for 1 mole of an ideal gas, we have PV equal to RT, isn't it? Now, how this equation it gets modified when we change various quantities? Let us see. What will be the equation for 1 gram of a gas? This is for 1 mole, na? What will be the equation for 1 gram?
So PV equals to W by M into RT.
W by M into RT.
So W is the weight of the gas given, and M is the molecular weight. Sorry.
What is the difference between weight and molecular weight? So you mean to say W is the total weight of the gas, and M is the weight of one molecule. That's what you are saying.
No, sir.
But that's not correct. No? That way you will end up getting PV equal to RT into number of molecules. But whereas the equation says is the number of moles. It is not the number of molecules. You will end up getting the wrong equation. No? Yes, they were very good. Now see. If V is the volume of 1 mole, okay, of gas, and M is the molecular weight, now small v, let me represent it by this symbol, small v. It is the volume of 1 gram of a gas. At pressure P and temperature T. So this is must, because this volume can change depending upon the pressure and temperature. Na? So we need to mention that this is the volume at this pressure and at this temperature. Okay. Because if we change the temperature or pressure, then the volume will change. Then the ideal gas equation for 1 gram of gas is P into small v R by mt, which is equal to small rt, where small r equal to capital R by m is a gas constant for 1 gram of a gas. So this is the equation. Okay. Is it clear?
Yes, sir.
Now, can anyone tell me what will be the equation for one molecule only? Only for one molecule. Yes, please. For one molecule. Concentrate on this. This is the equation for 1 mole. And in 1 mole, how many molecules are there?
So Avogadro
Sir, we
numbers.
will divide the equation by Na.
Yes, means if we divide this equation by Na, means right hand side, especially. So we will end up getting the equation for one molecule. Na?
Yes.
So for one molecule of a gas, PV equal to R by Na, where Na is the Avogadro number, and you might know that this is equal to KT, na? R by Na.
Yes, sir.
Isn't it?
Yes, sir.
Now for n molecules, we can multiply this expression by capital N. Is it clear?
Yes, sir.
So now let us calculate various quantities. First of all, universal gas constant. Let us see what does this quantity represent. What is this quantity in actual? So can you tell me the dimensions? Please put R in bracket over here. What are the dimensions? Theta I'm using for temperature. Okay. Now R is clearly PV by NT. So it is pressure into volume, N is number of moles, and then temperature. And pressure into volume is what? Work done. Na? You remember you represent work done by PdV. It was number of moles. Na? I wrote molecules. Number of moles into temperature. Please make the correction. If you have copied molecules, please make the correction. It was moles. But I spoke correctly, I think. While writing, I did the mistake. So it is work done by number of moles into temperature. Okay. So it is work done per mole per Kelvin. Na? So means SI units are of RR. Work done means joule per mole per Kelvin. Isn't it? Please check.
Yes, sir.
Yes, sir.
Now, can we get the value of capital R? Anyhow,
5.31 joule per mole per Kelvin.
how can you get that value? Now consider 1 gram at a constant temperature and pressure. Then PV by T, we know that, or you can simply write 1 mole. No need to write, consider 1 mole. We know that at STP, or 1 mole of gas, or all gases, it is standard. At STP, it occupies a volume of 22.4 liter. Okay, it means volume is equal to 22.4 liter. It means it is 22.4 times from minus 3 meter cube. Standard temperature pressure means temperature is 273.15 Kelvin and pressure is 76 centimeter of mercury. Isn't it? 76 into 10 to the minus 2, then density, then G. H rho G, na? Pressure is, remember this formula?
Yes, sir. Yes,
H is the height, 76 centimeter. So I have converted this 76 centimeter into meter. This is the density of mercury and this is acceleration due to gravity. That's how I'm putting various values. So now we can put all these values over here. P, V, T, and then we can get R. So R is 76 times from minus 2, 13.6 times per 3, 9.8, and of course volume is, and then temperature is. Now please get me this value. So you will end up getting that 8.31 factor. Joule per mole per Kelvin. Please check. Please tell me, are you getting this?
Yes, sir.
Yeah, 8.30 something. So we approximated it as 8.31. And now we can convert it into CGS units also. Because in CGS, that joule is related to as args or even related to calories also. Because calories are the favorite units whenever we discuss this thermodynamic part. Normally, it is in the form of calories. So 1 joule is equal to how many calories? Or 1 calorie equal to how many joules?
4.2.
Yes, 1 calorie equal to 4.18 to be
Yes,
exact.
sir.
But if you want, you can take it to be 4.2. Okay. So 1 calorie equal to 4.2 joule. So this shows 1 joule is 1 by 4.2 calorie. Therefore, in CGS system, R is 8.31, 4.2 calorie per mole per Kelvin. So approximately 2, na? Little less than 2. What is the exact value?
1.98.
1.98. Clear?
Yes, sir.
Now, what is the meaning of NTP? Let me tell you the meaning of various quantities, and then we will have information about Boltzmann constant also. What is NTP?
Normal temperature and pressure.
Normal temperature and pressure. What is the difference between STP and NTP? Yes. Any difference?
Here pressure is 1 atmosphere.
Pressure is
1 atmosphere.
What is that value? That is also the same, I think.
Yes, sir. 76 centimeter of mercury.
Yes, this is also 1 atmosphere. So where is the difference? No difference. Then why two types of units are there? NTP and STP.
Actually, till now we have learned they are same in 10 standard and 12 standard.
They are same. No difference at all.
So we have been learned that.
But there must be some difference, no? Nobody knows.
No, sir. Yeah, we don't know actually.
Normal temperature and pressure. Actually, in normal temperature and pressure units, the difference is that of temperature. It uses a temperature of 20 degree normally, but in different books they give it to be the different one. Okay, and normally they drop out that factor of 0.15 also. So can I write now? Temperature is 20 degree actually. So it is taken to be as 293.15 Kelvin. Pressure is only 1 atmosphere, that is same. So no difference regarding the pressure. Okay, so that is the difference. Normal temperature is 20 degree. Standard is 0 degree. Clear now?
Yes, sir.
Yes, sir.
So this is the difference. And please make a correction in your book also. It is given as 0 degree, I think, in your book. And volume is also same. The rest everything is same. The difference is only of temperature. Okay. And do you know this? What is absolute zero of the temperature?
273.1.
Minus 273.15. Only then it will become 0 Kelvin when you add 273.15 to this. And what is the definition? How you define absolute zero physically?
So at this very temperature, the gas becomes of 0 volume and 0 pressure.
It is the point where all intermolecular motion stops.
Yes, you can simply say that the gas, it gets frozen. No motion is there between the molecules at all. At absolute zero, all types of motion they stop. So the temperature, the minimum temperature we must say, because we are not going to get a temperature less than this anyhow. No? The minimum possible temperature at which all the gas molecules come at rest is called, or is defined as, absolute zero temperature. It is always 0 Kelvin, okay? That's why it is minus 273.15 degrees centigrade. No? And at this temperature, we say that the volume of the gas becomes 0. Clear?
So what about the pressure?
Obviously, when the gas does not exist, no pressure will be there. No? When the molecules are not moving, pressure is also 0. What is the source of pressure of a gas?
So the interaction force between the molecules.
So when nothing is moving, will there be any pressure?
No, sir, it's okay.
So Boltzmann constant, that K that we introduced, no? And if some of you are getting confused, no, what you can do is normally we put a subscript B to show that it is a Boltzmann constant. You can write it like this, okay? K with a subscript B means it is Boltzmann constant. Clear? So I will also do the same thing over here now. KB, it is small k actually. So what is its value according to you? First of all, dimension. Same dimension. Yes. R was 8.31. N Avogadro number. A means Avogadro number. Okay. So it will come out to be 1.38 times from minus 23 joule per Kelvin. Please check. Yes. So these values you need to remember. Okay. Now another quantity. What is specific gas constant? This is small r that we introduced in one expression. Let me tell you. In this expression. This is equal to R by capital M. What are the dimensions? Just remove M from the dimensions of R. L2T minus 2 theta minus 1. So R is R by M. Units are, SI units are Simply we can write units also. Joule per kilogram per Kelvin. Because now we divided by mass. Na? It was joule per Kelvin, so we divided it by mass. So it is joule per kilogram per Kelvin. And of course, you can go for erg per gram per Kelvin also. So of course, this small r, it is not a constant quantity. It has become variable now because m will be different for different gases. Na? First two are constants, Boltzmann constant and universal gas constant. But this small r, it is a variable quantity. Isn't it?
Yes, sir.
Now, let us discuss various gas laws. First law is Boyle's law. So these you have studied in detail in chemistry also in 11th standard. When you start studying chemistry now, in the very first chapter, you come across all these laws in detail. So you can revise that your 11th class chemistry book, okay? You will get some better idea. And of course, it will be easier to revise that way also. So for a given mass of an ideal gas, and of course, these laws are in your 9th standard also nowadays, if I recall. So for a given mass of an ideal gas at constant temperature, so we have made the temperature constant. So what are the variable quantities now? So there were three quantities only, P, V, and T. So temperature is constant. So it means now you write the equation all the time. So PV was proportional to T. Now this is constant. It means there will be inverse relation between volume and pressure. Okay. The only thing you need to remember is in Boyle's law, temperature is constant, and rest of the relation you can get from the ideal gas equation. Clear? Because this is constant, this is constant. So it means product of PV is constant, and that can only happen when one is inversely proportional to other. The volume of gas is pressure. That is V is proportional to inversely proportional to P, or PV equal to constant. Or it means P1 V1 is P2 V2 for a constant temperature. Clear?
Yes, sir.
So you can put it like this also. Can I write it as, because density is mass by volume, na? So volume is mass by density, na? So that's why I have replaced volume by mass divided by density. And of course, this gives me P by rho equal to constant, or P1 by rho 1, P2 by rho 2. This is another form of Boyle's law. This is one form, this is second form. Okay? Clear? Now third form. Can I say PV equal to P n by n? Because number of molecules per unit volume, small n, per unit volume, small n, is n by V. So this shows V is equal to n by n. And now capital N is constant. So it means it gives us P by small n as constant. Yet another form of Boyle's law. Okay? Please check all these forms. Are they clear to you?
Yes, sir.
Now we can represent all these expressions graphically also, and this can be asked in exam also. So let us plot various quantities against each other. So first of all, pressure versus volume. It was inverse relation. So the plot will be like this. And then what will be the relation between PV and P? And PV and V? And then pressure as one. PV and T is?
Parallel to the p-axis.
Yes, parallel to P-axis. Means constant. And what is PV versus V? Again same. P versus 1 by V. Sorry for this one. Actually, I'm not able to grasp. Now it's okay. Straight line passing through origin. And what is there for V versus 1 by P? Same. Please check everyone.
Yes, sir.
Is second, third clear? How it comes? Because PV is constant. So it is independent of pressure. And it means it is also independent of volume. So that's why in second and third graph, they are constant. They are not varying with variation in pressure and volume. And of course, now we can say that P is constant by V. So P is directly proportional to 1 by V. So that's why this fourth graph is there. Or we can put it in this manner also. V is constant by P. Means V is proportional to 1 by P. So that's why this fifth form of graph is there. That's how these forms are there. Please check everyone. Clear?
Yes, sir.
Second law. Charles law. Charles law. So if the pressure remains constant, the volume of the given increases or decreases by. Now, again, in some of the books, they drop out this factor of 0.15, but I'm retaining it. Okay. for each 1 degree centigrade rise or fall in temperature. It means volume at any temperature T, it is volume at 0 degree plus into 1 plus P by this factor. This is Charles' law. Degree centigrade, V at a given temperature T. This is the variation. Clear? This is the expression and this is the graph. At T equal to 0, Vt is equal to V0. And if T increases, volume increases. If T decreases, volume decreases. And when T becomes equal to this temperature, you can see this factor will contribute to -1. So 1 minus 1, it will become 0. Clear?
Yes, sir.
Yes, sir.
Let me write in detail. At T equal to 0, Vt is equal to V0 now. And at T equal to minus 273.15, Vt becomes V0. 1 minus 273.15 by 273. So it will become 0. That's how we are doing. Now, another form. If the pressure only at minus 273, now, earlier also we wrote this. You might have forgot. Read this. What we have written. We have already written this thing. That at absolute 0, the volume becomes 0. And that is exactly we are getting. This is absolute 0, minus 273.15. Okay? Is it attainable, Sanket? First of all, tell me. Can you attain absolute 0 by any means?
No, sir.
So that's why. So your question itself gives your answer. Because it is not possible, so that temperature, it is unattainable.
Yes, sir. Okay, sir.
Otherwise, we would have attained that temperature limit. So that is why it is not possible. Because it is not possible to remove all the molecules. Volume cannot be reduced to 0. So V is proportional to T, or V by T equal to constant, or it can be written in this manner also, V1 by T1 equal to V2 by T2. Of course, if pressure is constant. Now, what is another form? Can I write it in this manner? I already proved that V is equal to mass by density. So same thing I'm using. Okay? Clear or not? So can I say rho T equal to constant because mass is already constant? Clear? So now again graphical representation, just as we did for Wiles' law. Let us make various graphs. Now very first graph, volume versus temperature. So of course it is a straight line. And then 1 by volume versus temperature, and volume versus 1 by temperature. Please check. V by T versus T or 1 by T. Independent, because V by T is constant. And then 1 V by T versus V or 1 by V. Again independent. Again it is a constant quantity, V by T. So please check. All these kind of graphs are there. Clear?
Yes, sir.
And then Gay-Lussac's law. It is also called pressure law. Now in this we make volume as constant. Actually, we replace volume and pressure terms. Okay, this is exactly similar to your Charles law, only with volume and pressure exchange. Similar expression is there. Again, with volume replaced by pressure. Similar graph. Okay. So this is pressure law, Gay-Lussac's law. when you have to access the pressure or volume at some given temperature T, other than at 0 degrees centigrade. Clear or not, Arun? Suppose you are given the pressure at 0 degrees centigrade, but you have to make the calculation, suppose at NTP or some other temperature. So then you need to calculate the pressure at that temperature. Then you can make use of this expression. Actually, by using this expression, if you know the pressure at T equal to 0, then you can calculate the pressure at any temperature. That's how these relations, they are useful. Okay. Now, another form of this law. The volume remaining constant, the pressure of a given mass of a gas is directly proportional to the temperature. Yes, please check. So this is the relation we make use of. Yes, clear?
Yes, sir.
Is it clear or not?
Yes.
Nobody speaking?
Yes, sir.
Yes, sir. Clear.
Yes, sir. Clear.
So try to make the graphs yourself now with the help of these relations. Again, 5 graphs will be there. Of course, first graph between P and T. Then, of course, 1 by P versus T. And then P versus 1 by T. And then P by T versus P or 1 by T. And then P by T versus P or 1 by P. Like this, now. So first is P is directly proportional to T. So a straight line. And this will become inverse relationship. This will be, both will be inverse now.
Yes, sir.
And it will be a constant.
Parallel.
Yes, both are constant now. Because P by T is the quantity which we are calling as constant. So it is not varying at all. So these are the straight lines actually. Not, yes, now it is okay. So here this was third law. Now what is fourth law? Avogadro's law. And what is that law? Equal volume of all the gases under similar conditions of temperature and pressure, they contain same number of molecules, no? Or equal number of molecules. Okay. So this is the law. Next, Graham's law of diffusion. Graham's law of diffusion. It says when two gases at the same pressure and temperature are allowed to diffuse into each other. Diffuse means mix. Means suppose you have made a partition between a room, and on one side of the room you are having, suppose, oxygen, and on the other side you are having nitrogen, and then you remove the partition. Then both the gases, they will diffuse into each other. Diffusion means the molecules of one gas, they will float towards the other gas. That is called diffusion. And it happens because of the concentration difference. Because on one side we are having oxygen only, and on the other side we are having nitrogen only. So both the gases, they will float till equal number of gases are present in both the halves. Okay. So the rate of diffusion square root of the density of the gas and from where does this relation comes? Of course, we will be studying it later. It will come from kinetic theory of gases, of course. But right now, you can write that rate, mathematically, this rate, it is like 1 by rho, square root, or a rate of two gases. It is in this ratio. Later on, we will prove this from kinetic theory of gases. And what is another law? Last one. Dalton's law of partial pressure. The total pressure non-reacting gases. So there are different gases in a vessel, and the gases, they do not react with each other. So you can think of the inert gases. Okay, so a vessel is equal to the sum of the individual pressures which each gas would have exerted if it would have been present alone in that vessel. Okay, so for n gases we have P is equal to pressure of first gas, second gas, third gas, up to nth gas. So this is the pressure exerted by mixture. These are the partial pressures. Clear?
Yes, sir.
So now let us start discussing the kinetic theory of gases, the main thing, okay, which we have to discuss today. So all these were the basic things and that are required in order to discuss the kinetic theory of gases. And of course, all these things, they can be proved with the kinetic theory of gases. And this is the basic, you can say, of the kinetic theory of gases. Okay. Only then we can call it as kinetic theory, if it is capable of explaining all these laws. So now, of course, every theory, it has some, you can say, assumptions. It has some limitations. So what are the assumptions of kinetic theory of gases? Means the theory will be valid only under certain conditions. So first of all, as we discussed earlier, this kinetic theory actually, it is a bridge between the macroscopic properties of a gas and microscopic properties. It links those two properties together. It gives us a mathematical relation between the macroscopic properties, that is pressure, volume, temperature, and its microscopic properties. What are the microscopic properties? The properties related to the gas molecules itself, their speed, their momentum, their kinetic energy, etc., etc. Okay. So kinetic theory of gases relates okay. So in actual practice, it attempts to develop a model of the molecular behavior, that how the molecules of an ideal gas, they will behave. Okay, so this is the summary of this kinetic theory of gases. So it is based on the following assumptions. Means we are trying to develop a mathematical model for the behavior of the molecules of gas. And that is what we call as kinetic theory of gases. So every gas extremely small particles known as molecules. And all the molecules of a gas are identical. And of course, these are different for different gases. And then we will take the molecules to be spherical, rigid, and perfectly elastic. Only then we are able to explain the pressure exerted by the gas. Now. Okay. The molecules of a gas are spherical, rigid, and perfectly elastic point masses. Means collision between the gas molecules, it is taken as perfectly elastic. We assume that no energy is being lost during the collision. Point mass means their size is negligible in comparison to the intermolecular distance. Okay. And they keep on moving all the time. They are never at rest. They keep on moving randomly in all possible directions. And with all possible velocities, it means different molecules, they have different velocities. Of course, there may be many number of molecules having same velocity also, but I mean to say there are lots of group of molecules having different velocities. And that we will study in molecular distribution of velocities. Okay. And then the gas molecules keep on colliding among themselves. Of course, a number of questions can be made only on these assumptions. Okay. That when kinetic theory of gases is valid, or what is true according to kinetic theory of gases, like that. Keep on colliding among themselves as well as with the walls of the container continuously. Container or vessel. And as I said earlier, these collisions are assumed to be perfectly elastic. And what do you mean by perfectly elastic collision?
Coefficient of elasticity is equal to 1.
Yes, the energy is conserved. In simple terms, the energy is conserved. And next important thing is, we assume that the molecules, they always travel in a straight line. They do not get deviated from their path. Okay. And the distance covered by the molecules between the successive collisions, it is called free path actually. Suppose one collision it is occurring over here, then it is moving here. So in between this distance, there is no other collision occurring. So it means during this distance, the molecule it is said to be free. It is not getting collided with any other molecule or container. So that is why it is called free path. And of course, for the complete journey of this particle, there will be many more free paths like this. Na? So we always take average of all those free paths, and that is called mean free path. Okay. So you can see a lot of assumptions are there. Means the collision occurs for small interval of time. Means this is coming, colliding, and then immediately it is going away. Means it happens just within fraction of some nanosecond or picosecond. The particle, when it is colliding with another particle or molecule, when it is colliding with another molecule, it does not stop over there. Okay, so that time is negligible as compared to the time taken by the molecule to go from one particle to another particle, or from one molecule to another molecule. That's what we are saying. Comparison to the time between two successive collisions. And the important point is the number of collisions per unit volume, they are always constant. Number of collisions per unit volume okay. Last point is the density of gas is constant. Means uniform distribution of the molecules we are assuming. And assuming all these assumptions, we can get the pressure exerted by a gas, ideal gas. So I will be writing the formula straight away, of course. Okay. So what is the formula for the pressure? By an ideal gas. So it is given by 1 by 3 mn by v, v RMS square, v RMS square. N are the number of molecules, mass of each molecule. Of course, v is the volume, and VRMS is the root mean square speed of the gas molecules. And let me write it on the other slide. Note it. So VRMS is the root mean square velocity of the gas molecules. So always remember the reverse. Do the reverse of this root mean square. So now do the reverse square. It means do the square of the velocities of the molecules and then take the mean of them and then take square root of them. Root mean square, mean, then mean. So mean of the square and then square root. So this is the definition. And then this way you end up getting this formula. So I have squared them up. You can see sum of squares of velocities of all the particles. And then I'm dividing it by number of particles. So this is the mean. And now if I take the square root, this becomes VRMS. No? This is the volume of the gas, clearly, capital V. Okay. Volume of the, you can say, gas or container, it is same thing, because gas is inside the container. Okay. Okay. So now the meaning of all the quantities, it is clear.
Yes, sir.
Yes, sir.
So you should remember this expression now. This is very important. And the definition also. Okay. So what is the way to remember? Root, mean, square. So learn the opposite. Now do the opposite. Square. So I have squared the velocities and then I have taken their mean. And then a square root is there in that. Okay. So it is always the reverse. Like this. Okay. So now we can again put it in various forms. So it is 1 by 3. Can I write it as m by v, VRMS square? Or let me start from the beginning. What was the formula? Mn by v. No? So what is the constant quantity in this expression? 1 by 3. And VRMS, do you know the expression for VRMS? VRMS square is always proportional to temperature. No? So that we will study later. VRMS square is proportional to temperature. No? It is of the form some constant into T by pi, by mass, sorry. Pi is there in that average. No? Okay? Clear?
Yes, sir.
Yes, sir.
There are three kinds of velocity. Na? Average, most probable, and VRMS. VRMS is 3 kT by m square root. Okay? Most probable is the least of them. It is 2 kT by m square root. Then average 8 kT by m pi square root. It is like this.
Yes, sir.
Okay? So that we will study in molecular distribution of velocity. Okay? So that is all for today, students. So we will continue from here. Okay? So please revise all this because we have started with this topic today only. So now you can revise it. Those students, especially those students, those who have joined late now. So please do the work regularly and go through the recordings also every day. Only then you will be able to complete the syllabus. So okay, students, bye bye. Take care.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.